Okay, so here we have an infinite sheet, like an infinite piece of paper carrying a current. In my picture, I've got my current flowing up. So we could imagine this as a whole bunch of wires all glued together, all with the currents flowing up, straight up there. Now, because we have an infinite number of wires, we technically have an infinite current. This is an infinite sheet. It goes on and on forever in that direction and up and down. So we can't say we have total current I. I is infinite. So we have a current density that's measured in amps per cross-sectional dimension, in this case meters. So our current density is in amps per meter. So we're going to need that to find an I enclosed at some point. That's the tricky part, is thinking about units to find I enclosed. So because we have this infinite sheet, we can use symmetry to make the argument that the magnetic field can't possibly depend on my position, say, in this direction. The magnetic field here should not be different than it is here, or up and down. The magnetic field should not be bigger up here than it is down here. This thing goes on forever up and down. The magnetic field could only possibly depend on my distance from the sheet. Another argument we can make is the magnetic field has to point parallel to the sheet but perpendicular to this up and down direction. So if the sheet were your computer screen, the magnetic field would have to point left and right. It can't point toward the screen or away from the screen, or up or down. It would have to point left or right. Because think about this. Let's look at this sheet from the top. So we're kind of like right in the middle of the sheet. Here's the sheet. And think of it as a bunch of wires glued together, all pointing right at your eyeballs, and the current's coming straight out at you. So think of this wire right here. His magnetic field, just that guy right there, would go in circles using the right-hand rule like this. So over here, he would have magnetic fields that point up, over here down. Well, this wire is going to have the same thing. This one's going to have the same thing. So this guy here, right there at that spot, him, might have a magnetic field that points in this direction. Well, this guy here would have a magnetic field right there that points in this direction. Those two components back and forth would cancel. Everything would equal straight up. So the magnetic field on this entire half of the universe has to point up. Over here has to point down. It has to, just by symmetry. So I'm going to draw an Empyrean loop that exploits that symmetry. I want nice square edges. So my Empyrean loop, I hope you can interpret my picture here, is a rectangle that cuts perpendicularly through my plane, juts out a distance r. So this would r backwards behind the plane, r in front of the plane. That's supposed to be the intersection of my rectangle here and the plane, and has length on this side L. So here's that top view. So the plane, we're looking at the top of the plane, the current's flowing out towards our eyeballs. And here is our Empyrean loop. We're going to traverse it in this counterclockwise direction because I know B flows up over here and down over here. So my DLs, see the little reds here? All the DLs flow around like this. Right there, DL points to the left. Down here, DL points to the right. On this side, DL points up, and on this side, DL points down. Then Ampere's law says the loop integral around that entire Empyrean loop should be mu naught times I enclosed. I have 4 different segments here. I'm going to have to do 4 integrals. We've got section 1 up here. Remember, B is pointing up on this whole section here. B points up, DL points to the left. Over here, B points down, DL points to the left. On that entire section, all of one up here, B and DL are perpendicular. Same thing down here on section 3. DL points to the right, B over here points down, up over here B points up. That's always perpendicular to DL. On 1 and 3, B and DL are perpendicular. The dot product of perpendicular vectors is 0. So these two here have no contribution to that total integral. 1 and 3 contribute nothing. What about 2 and 4? B points up, DL points up. Those are parallel. Similarly over here on 2, B points down, DL points down. Those are parallel. The dot product of parallel vectors is the product of the magnitudes. So on 2 and 4, B dot DL would just be magnitude of B times DL, or the integral of DL. That's just the length. How big was this side here? L. Here's side 4. This back here was side 2. Here's 1 and 3. So integral of DL is just the length of this side. So I get an L here. And I get another L from this side. So all the way around this entire integral, I get 2 zeros and 2 L's. Integral around the entire loop of B dot DL is 2L times magnitude of B. That's supposed to be mu naught times I enclosed. How much of my current is enclosed? Well, since J, like you can just look at units here. Since J is current per unit length, the intersection of my cross-sectional area here and my sheet is just right here. It's just that right there. It's that length. J times meters would give current, amps. So my current enclosed is J times L. So 2LB equals mu naught I enclosed. That's mu naught JL. The L's cancel. If the L doesn't cancel, I've done goofed. I know my final answer could only depend on R. It may not even do that, but it can't possibly depend on this parameter I made up. The L better cancel or I goofed. And it does. And look, it doesn't even depend on R. Just like the electric field from a sheet of charge was constant everywhere in space, the magnetic field from a sheet of current is constant everywhere in space. It's a vector that points parallel to the sheet and does not depend on the distance from the sheet.